I will begin once I get up here. So let me begin with a word of prayer. Heavenly Father, we thank you again for your many blessings, and just pray that you'd guide us today, help us to glorify you, what we do, Lord. In your name I pray, Lord Jesus. Amen. So I just wanted to play around with some matrices here for a couple minutes, and then I will let you guys play amongst yourselves. I mean, hopefully you have been working on the computer project, and hopefully it makes sense to you, or hopefully you can find somebody it makes sense to, and maybe they can help you. But what I want to talk about is just about like how we could use matrices to create objects. So you guys know complex numbers, right? How do they work? We have what, like a plus ib times x plus iy. How does that work? We got ourselves like, you know, ax minus by plus I times, let's say, bx plus ay, right? So what if we think of here x plus iy like a column vector, right? If we think of it that way, then what is, if this is what we're saying, right? If this is thinking of a complex number as a vector, right, in the plane. So you guys tell me how to do my right hand side of the equation. Like I can rewrite, this is actually what? This is just a sneaky notation for the column vector ax minus by, right? bx plus ay, right? And so, hey, can you rewrite that as a matrix multiplication times xy? I think we can, right? Like, here, I'll get us started. So this is equal to a particular matrix times xy, right? What's that matrix? A minus b plus, yeah, b and a, right. So, well, this is interesting, right? So maybe we should say definition. The matrix that corresponds to a plus ib is equal to a minus b, a, right? And I mean, we can play all kinds of games with these kinds of matrices to try to understand what do they tell us about complex numbers. I mean, let's see here. Like, let's take this out for a spin, right? Like, what's the matrix that corresponds to the number 1? Yeah, you put a equals to 1 and b equals to 0. You get 1, 0, 0, 1, right? And what's the matrix that corresponds to the imaginary unit? Now try that out. Does that matrix, how's that matrix work? Like if we call this matrix, I usually call it J. What happens if we calculate J squared? Let's see here, we get minus 1, 0, 0, minus 1. Hey, that's minus the identity matrix, isn't it? So one way to look at this is if somebody comes to you and they're like, you can't talk about the imaginary unit, there's no such a thing, right? There's no such, you can't have something that squares back to something that's like negative the multiplicative identity. I mean, these people won't say that. Don't say those words, but put those words in their mouth. and then show them this matrix. There is such a thing as a matrix which squares to -1. It's very much real. It's a real 2 by 2 matrix. That's it. What if you were to calculate the inverse of this matrix? Let's say A plus IB inverse. We have a formula for that, don't we? This is a 2 by 2 matrix. What's the inverse of A minus B, BA? What's it equal to? We know this, right? That 1 over the determinant. What's the determinant of the matrix? And this, it looks like A squared plus B squared, right? Flip the diagonal, nothing happened. Minus is on the off diagonal, right? Can you tell me what that is? I mean, of course, we can rewrite that as A over A squared plus B squared, B over A squared plus B squared, minus A over A squared plus B squared, right? And A over A squared plus B squared, right? That's the matrix of what complex number?
That's correct.
Uh-oh, what'd I do?
It's the bottom left element of the matrix.
Oh, I think I've got the wrong letter, right? Yeah, thank you. Good catch, Nolan. That should definitely be a B. And that makes this a B. Yeah. Thank you. But that's the matrix of what complex number? I don't know if you guys remember this or not, but 1 over A plus IB, right? It's A minus IB divided by A plus IB times A minus IB, right? We multiply by the conjugate over the conjugate, and that gives us A minus IB over A squared plus B squared, right? So what we're looking at is the matrix of the inverse, the multiplicative inverse of the complex number, right? To summarize the calculation I just did, I showed you that the matrix of the complex number Z inverted is the same as the matrix of the inverse of that complex number. But there's a profound difference between the left-hand side and the right-hand side of that equation, right? The left-hand side, I'm talking about the inverse of a 2 by 2 matrix, which we know from this semester, right? Or maybe high school. Seriously, if they didn't teach you that in high school, you should demand like a refund or something. Something like that. And then on the flip side, on the right-hand side, that's the inverse of a complex number, right? Does this correspondence between matrices and complex numbers that I've used big M to denote, do you think it has other properties? Like, we can try it. I won't prove these, but you could show, in fact, that like the matrix, if we let it act on Z plus W, guess what? You get the matrix of Z plus the matrix of W. You can prove that if you've got the matrix of a product, Z times W, that's the product of the matrix of Z times the matrix of W. Like that. That's also another property of this map. So what this thing does is it trades the complex algebra for corresponding matrix algebra of these special matrices. But another way to look at it is it's giving us a concrete model of complex numbers as 2 by 2 matrices. We could do the same thing for quaternions. We could find 4 by 4 matrices which correspond to quaternions. The way that would go, basically the same kind of calculation, but we'd have to do, oh man, great googly moogly, A plus IB plus CJ plus DK, I'm going to regret this, T plus XI plus yj plus zk using the quaternionic multiplication we talked about last time, right? So I'm just gonna, okay, so we've got AT rather, minus bx minus cy minus dz, because I squared equals to j squared equals to k squared equals to minus 1, right? Then I get plus, let's say, a times x, all right? And what I'm going to do is I'm going to factor out the I here. So you guys tell me, AX has obviously got an I next to it, right? What would come next? Do you remember the rules we talked about? Just like Calc 3, right? Like, how did it go? I mean, well, the easy one, of course, is we have a times x, that gives us an I, but there's also a t times b, right? So I should probably put that one first. bt plus ax, that would have been smarter. What are the two other ways we can get I from this product? J times k, right, is equal to I, and k times j is equal to minus I. Them's the rules, right? So this j with this k gives me a cz. Probably should put that last. And then I've got a minus, oh man, lost track where I was. Rats. Dy, okay. Here's a hint. If we wrote the right formula, we should have all the letters in every line, I think. I've got my t, x, y, and z. I've got my a, b, c, and d. Okay, we're good. Next up, the j terms. All right, I'll do the easy part. B, rather c times ct plus ay. I really should put that next, but I'll put it there. Fine, I won't. I'll put it over here. We'll leave a spot there, plus ay. All right, but we also, how else can we get j? We have k times I is equal to j, and I times k is minus j, right? So ki gives me dx, and then missing my b minus bz, right? And then finally the k terms. I've got dt plus az, and then remember ij is k and ji is minus k, so that gives me, let's see here, I get by, put that over here, and I get minus ax, no, not a, it can't be a, it's got to be what? C, right? J times I, cx, yeah. Ow! So, if we use the notation, right, that this, right, is really just another way of writing the four component column vector t, x, y, z, right, like an element of R4, okay? Then with that notation, this multiplication works out to what? Like we've got, you see we've got AT minus B. If you don't mind, I'm going to skip a step and just write down the answer because I'm tired of writing all this, right? So like, what do we got? What 4x4 matrix do we get? Some 4x4 matrix times t, x, y, and z. So I put, to get the first one, I put my A minus B minus C minus D. Then I've got B, A minus D, C. Then I've got C, D, A minus B. Then I've got D minus C, B, and A. That I would call, right here, the matrix of the quaternion A plus BI plus CJ plus DK. And there's all kinds of secrets hidden in this matrix about quaternions that are really nice. Like in the previous, my first example, you notice that we had the determinant of the matrix of A plus IB. What was it? Remember, it was A squared plus B squared. We saw that in the formula for the, the inverse over here. That's the length of the complex number squared, right? So if you believe in the niceness here, what do you think the determinant of the matrix of the quaternion is equal to? We have a winner, yes. In other words, it's the length of the quaternion thought of in the Euclidean sense. It's just the length squared of the quaternion. And, oh, shush. Just a scam. It's one of the, I guess more and more scam numbers. Anyway, so, and by the way, you could prove that the matrix of a quaternion, say eta, times the matrix of a quaternion, say beta, is the matrix of eta times beta. This is also a property of the quaternion map. So what does that mean if you take the determinant of this? We've got the determinant of the matrix of eta times the determinant of the matrix of beta, because we know properties of determinants, right? Is equal to the determinant of the matrix of the product, the quaternionic product of eta and beta. But what does this say? This says that the length of eta squared times the length of beta squared is equal to the length of eta beta squared. In other words, quaternions are like complex numbers. They're set up so that when you multiply two quaternions, the length of the product is the product of the lengths. That's actually really interesting. But it goes to sort of make good on some of the promises I was telling you last time that, well, some of the motivations of Hamilton to discover the quaternions was exactly this, because this is part of what makes complex numbers such a good descriptor of two-dimensional geometry is exactly this property, and it's shared by quaternions for four-dimensional space. If you were to study algebras in the abstract, you wouldn't find this, right? Like a different multiplication in 3 dimensions, for example. You can look at R3 as like 3 hyperbolic numbers, as I call them. So things of the form x plus jy plus j squared z. Not the same j, by the way, guys. Here, j cubed is equal to 1. If you look at these numbers, I call these quote-unquote 3 hyperbolic numbers. Technically, it's the real group algebra of the cyclic group of order 3, whatever that means. And if you look at this and you look at you do the same calculation we just did with respect to the multiplication of this thing, all right? What you find is that the matrix representative of something like A plus BJ plus CJ squared, it works out to A, B, C, and then you get C, A, B, and then you get B, C, A. That's the matrix representative of a 3 hyperbolic number. And now the determinant doesn't have the same, it's not directly connected to the length of this thing as a 3-dimensional vector. The determinant of this actually is equal to the following. It's, goodness gracious, a cubed plus b cubed plus c cubed, I think minus 3 times abc. I think that's it. And if you tilt your head and squint, you can see that this factors as a plus b plus c times a squared plus b squared plus c squared minus ab minus ac minus bc. I mean, I never saw this, but I had a student who saw it. Min's like, I factored it. I'm like, what? Yeah, I factored it. Like, what do you mean you factored it? I factored it. Goodness gracious. But this is actually well known if you study things called symmetric functions. It's not surprising that this happens. Whatever happens, there's an interplay between a, b, and c here. They appear symmetrically, so like formulas that come from calculating the determinant have to bear out that same sort of ABC exchange symmetry. And so they have to be written in terms of the symmetric functions in a, b, and c, which these are 2 of. Anyway, I think this is right. I'm going off memory, but it is still true that if we, had the matrix of one of these, right, and the matrix of another one of these, it would be the matrix, like this is still true. It's still true that the matrix that represents the algebraic number, it implements the multiplication as matrix multiplication. So which one of these numbers are invertible? How would you check for invertibility? I'm telling you it's still true that also the matrix, and you can see this in my formula, what's the matrix of 1? That puts A equals to 1 and B and C 0, right? So you get the identity matrix. So look, for that number to be invertible, we need this to be not equal to 0. When would that expression not be 0? Like what could make that 0? Think about it. Anything on this plane, a plus b plus c equals to 0, right? So it's the plane with normal vector 1, 1, 1 in ABC space. Everything in that plane makes the determinant 0, right? That takes care of this factor. How about this? Could this ever be 0? If you study this, what you'll find, and you could study this using the quadratic form stuff I taught you this semester. You could write down the quadratic form. This is, what's the quadratic form here in ABC space? It's what? 1, 1, 1, minus 1/2, minus 1/2, minus 1/2, minus 1/2. I mean, this is what I did to study it. Like that's the matrix. If I call this piece Q, let's say, Q of ABC, right? This is the standard symmetric quadratic standard matrix of that quadratic form. And if you study this quadratic form, you can find out that I think it only has, I think it's got a complex eigenvalue if I remember right, and one real eigenvalue, which is 0. And the eigenvector is actually 1, 1, 1, which is to say that the only way to make this expression 0 is to go through the normal line. So what this means is that every number in the 3 hyperbolic numbers is invertible except this plane and its normal line of numbers. These are not invertible. In contrast, the quaternions, Which quaternions are invertible? We have the determinant formula right there, a squared plus b squared plus c squared plus d squared. How could that be how could that be 0? What would you need for the quaternion a plus b j plus bi plus cj plus dk to be, have determinant 0? You'd need every single one of a, b, c, and d to be 0, which says that every non-zero quaternion is invertible in the multiplicative sense, just like complex numbers. So that's why quaternions they're almost what's called a field, right? But they're not commutative, so they're technically not a field. This, on the other hand, is much nastier, because you have like this whole plane and the normal line of what are called zero divisors. And I've studied calculus over sets like this, guys, and it turns out that calculus is rather yucky because of the zero divisors. Like, there's all kinds of places in calculus when you study the arguments where we use division by a number somewhere, right? Every place you do that requires qualification if you're working with numbers like this, because you cannot divide by anything that makes this 0. You just don't have a notion of divisibility. But anyway, I just wanted to give you guys just a tour, a little bit of some of the algebra I'm interested in. And every so often students work with me on it, but that's all I got for you today. Listen, so do you have any questions about the, don't worry, it says something about, the wedge product and tensors in the course planner. That's an empty threat. All right, I won't do that to you. You're okay. It's safe. And if you're interested, I can show you the slides about modern physics today, and we could just not have class Thursday if you'd like. What's your preference? Actually, you probably should have class so you guys can talk to me about the final, right? So we can just talk about the final either today or Thursday or both. Whatever your preference is. I think it's best though for you guys to use the time to try to finish your work on the computer project. Yeah. Do you guys have any questions about the computer project? I can get it out and we can talk about it together if you want. Would that be good? Okay. I see some hesitant nodding. You're like, I wasn't. When is it due? When did I say it was due? Did I say when it was due? Better question. Let's see if I can find it. Man, it seems like forever ago I wrote that thing. Let's see here. I meant to give you guys back the quiz 2. I think it's in my office somewhere. I don't know where. I was trying to find it before class and I just couldn't find it. But I've given you guys the credit for it. My folder for this particular course is especially bad because for some reason I decided, I don't need to separate things by semester. I'll just put it all in one big folder. Mistake. Definitely need to separate by semester. All right. Come on. Uh-oh. Excuse me. Goodness gracious. Whoa, what's that? That was not a good sneeze. A good sneeze is the one I can stop. All right, so now I have written all of this with the assumption you're using MATLAB, but you could use something else. But if you do, need to document it. So I fed it into ChatGPT, and this is what happens is not an acceptable answer. I fed it into Grok, and this is what happens. It's not unacceptable. And you continue inserting generative AI programs I don't know about here. I'd like for you to use, like software. You could use a website if you found one. I'm open to that. Anyway, so what I would do personally with these is, first of all, try to get my bearings, like what's the deal with this matrix? Like if I could figure out what the eigenvalues were of it, then I'd know what I'm looking for, right? Because if you find the eigenvalues, then you can like do row reductions on the A minus whatever the eigenvalue is, right? Like for instance, this one, if I can cut and paste, which is debatable.
That's very convenient eigenvalues. Very nice.
Let's see if I can actually just cut and paste that into. Try not to open up an email. Let's see here. So if we go to my favorite silly website. Actually, this is not silly. What am I talking about? Oh, come on. Oh, see what happens. Now, fine. Which I think means you didn't put them in the right format. Oh, phooey. Oh, goodness. Anyway, I'll let you tell us. What are the eigenvalues?
Well, as long as what I got was right, they were 6, 7, and 6 and 7, each with a multiplicity of 2.
That sounds like too much of a accident to be an accident. So, all right, so then what you probably need to do to fully understand it is to look at like what's A minus 6i and look at A minus 7i, right? And try to understand what's the null space of those, right? How would you, of course you can use the built-in, and I don't mind you using the built-in eigenvector commands in MATLAB, like read the documentation, learn how to use them. And there ought to be, I would assume MATLAB can also do generalized eigenvectors, but it's going to require more nuance. Yeah, it's not built in. It doesn't immediately think our thoughts. Yeah, that is true. But I believe in my heart that there is a generalized eigenvector routine in MATLAB. I just don't know what it is because I'm not a MATLAB expert by any stretch. Yeah, so that would be my advice, is like as a starting point, figure out what the eigenvalues are. That kind of knows what you're looking for. It helps you know what you're looking for. A Jordan basis, what is that? You're looking for, so, you said we had eigenvalues 6 and 7, and they're both repeated, right? That means that there are at least 2 eigenvectors to put in the Jordan basis, right? Now, what are the possibilities? Wait, this is a 5 by 5.
Yeah, so there was 67.
Oh, okay, so there are at least 3 eigenvectors we can expect from the theory, right? Eigenvector with 6, an eigenvector with 7, and an eigenvector with 67, right? Now, so you need to find those vectors, right? And then the question is are there enough eigenvectors to fill out the basis? Like, because if there are, it could be diagonalized, right? I don't remember what I did, but odds are high that it's probably not diagonalizable, if I had to guess. Anybody work it out yet? Yeah?
I got some generalized
2 generalized eigenvectors. So we have, in summary, what you found was there's 2 chains, one for 6, one for 7, and there's a 1 chain for 67. And so you put those together, that's your eigenbasis. And what you should find from actually calculating, and this is the beauty of doing this in MATLAB, is we can actually just let MATLAB do the inversion, right? You set up the matrix, multiply it out like that, and you should be able to get back to the Jordan form, like a 2 block for 6, a 2 block for 7, and the 67. All right. I was going to say, you don't actually This, I don't expect you to do this in MATLAB. Like if you try to do this in MATLAB, that just makes your life much more difficult. You can use the theory that we've done this semester to do that. All right? That's fine with me. Matrix exponential is very forgiving. The matrix exponential of blocks is the blocks of the matrix exponential. For like this, if I have e to the t times like a direct sum b, like this, that's e to the ta direct sum e to the tb. It works like that. So you can just basically take the matrix exponential of each block and then take the direct sum of those in order to find matrix exponential of your big matrix. The other thing that is super helpful is that if you have beta inverse times e to the ta times beta again, then again, property of the matrix exponential, this is t times beta inverse a beta, like that. In other words, if you similarity transform the matrix exponential by the Jordan basis, you'll get the matrix exponential of the Jordan form. And since the matrix exponential of the Jordan form, I actually have formulas for those in the notes. We talked about them in class. There's stone cold formulas for these. You don't have to work them. So, and my point is, you don't have to suffer through the indignity of trying to get MATLAB to do this symbolically, which is, as I recall, perilous. Like, I did have a Math 221 try to do that, I think, a year and a half ago, and as my memory serves, it can be done, but it's very unstable. Like, some groups got it to work, some groups didn't. It was kind of a hodgepodge. And so, I mean, that's my larger advice to you is make sure you know kind of where you're going. Do some exploration with the website we were just poking at, so you know what you're looking for. So if things go wrong, you know that your code is messed up. You guys can work together, right? So maybe pay Micah for the solution. I don't know. But my son was always trying to sell his solution to other students, but yeah, mostly Violet. But so did you? Whoa, this one. These numbers look suspiciously large. I must be up to something here. I have a suspicion that there's more. Well, you know. If I had to guess. So once you find the complex Jordan form, you use the real and the imaginary parts of part of that basis to make the real Jordan form. That's what we talked about. So the complex Jordan form is like the beta will be complex, a complex matrix, right? And the gamma is related to beta, but not directly. Like, basically, you only need half of the chains because we're talking about a real matrix, so the complex chains always come in conjugate pairs. So you pick one of them and take the real and the imaginary parts of each vector in the chain and then string those out. That will give you the real Jordan form, which looks an awful lot like the matrix I have covered up with the projector right now, right? It's almost the same. What was the difference? If we're looking at the real Jordan form corresponding to eigenvalue a plus ib, the minus goes down here, but it's almost the same thing, isn't it? Let's see here. If there's anything else I was going to tell you. This one's kind of fun. We haven't talked about a square root of a matrix, but I didn't want to put that on you until we actually had a computer to use, because these calculations get rather, Well, anyway, I guess I'll let you guys work. This one here requires something called coding, so you'll actually have to, I'm not trying to say that you need to type out, all 10,000 entries, because 100 by 100 is 100 squared, and I think that's 10,000, right? Yeah, so obviously you need to code this. You can't just do it. I guess if you're a glutton for punishment, you maybe could do 10. That's just 100 entries, right? But you notice that I made the n equals 100 worth 6 points. That's because it requires a certain effort. Now, some of you are like computer people, so coding this shouldn't be too much of a lift, I think. Just warning you, that's there. You know, it's not like everything else. It's well, anyway, trying to figure out, I think I've told you the main things. I'll let you guys play around with it. We never did say when this was due, did we? Did I say? I must have said in the announcements, right? Surely. Thursday. That seems. When would you guys like it to be due? I don't know what other options we have besides Thursday, though, is the thing.
December 1st.
December 1st. Wait a minute, that's yesterday. Let's see here. Do, 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 do. There are 7 points bonus, which means if you don't figure out the coding thing, it doesn't have to count against you if you have everything else perfect, right? Just saying. On the other hand, it's nice to get points that, you know. Do I ever say in this silly announcement when it's due? I did say Thursday? Okay. That was the next announcement. All right. Well, anyway, let's make it due Thursday. It can be due Thursday end of class. Would that be good? I'm not planning to go over its solution in class or anything. So Thursday, we will just talk about the final exam. And I really don't usually have anything very structured planned for that meeting. It's pretty much just an opportunity for you guys to ask questions about any of the assignments this semester, anything you're still unclear on how to calculate. We can go back and, you know, try to make sure we have all our ducks in a row. You know. If you ask me what one thing many students have wrong that they need to fix, in terms of people who need to fix things, I would say probably it's find the basis for the null space. You know, finding the complete solution set to AX equals to 0 for a matrix, right? Because that is also the eigenvector calculation, right? That's a big chunk of what we've done this semester, and it's, if you're a student who's struggling, odds are high that's part of it. So I would, if I were you, I'd focus some attention there. And of course, go back and look over your tests, see what you got wrong. You can talk to me in office hours, whatever, but yep.
Can we get like a note card or
Yes.
page or something?
It says 2 note cards, right?
That was at 5 numbers.
No, it says 2. I swear it says 2 on the front.
I think it said open internet.
It said bring your own chat GPT. Instructor, you know, I have long argued that, you know, if we're really serious, so they talk about S rates sometimes, which is the success rate of classes, which is based on the number of students who do not get a D, W, or F in it, you know. And I have been saying for a long time that if we just let professors take all of the exams for the students, we could fix the S rate overnight. I mean, I know the solution, but
I think we should write a final.
you should write a final. You guys would write a final for me. I'm scared what students would do with that. I don't know. I feel like it wouldn't be math. It wouldn't be math. It would just be like forcing me to write a, you know, I don't even know. I want to give you ideas. Let's see here. Oh yeah, 2 3x5 formulas. Yeah, that is what I said. But given the amount of material in this class, like I think I'm fine with a page of notes for the final. You know, given what we did this semester. So if you prefer, just have 1 page of notes front and back. That's fine by me. So, all right. Okay. Well. Yeah, front and back. Not just 2 sides. Yeah, okay. It's right here. Do. So I guess I'll see you guys Thursday.